So I talk about cosmology, what we call the large-scale structure of the universe, so the galaxies and how they formed, how the universe has evolved since the Big Bang, but also black holes. And black holes, and they're really evocative things. I think everyone's heard of these strange things, these totally collapsed stars, from which nothing apparently can escape. But in the past few years, past few decades really, beginning work that Stephen Hawking really began back in the 1970s and many others, we've begun to suspect there's a lot more to them. And they've started forcing us to reassess our understanding of what space and time are. And that's a really weird sentence. You might think, well, space is the arena in which we live and time just ticks, but it really isn't. It looks like, from studying these things, there are building blocks of space and building blocks of time. And so black holes, they're kind of a metaphor in a way, that by studying them, we're beginning to get a deep picture of what our reality actually is. That's a remarkable idea, but it's a beautiful idea that runs through all of science. But it's just a region of space from which even light can't escape. So Stephen Hawking, back in the 70s, calculated that black holes, they glow in the sky, like coals in the sky, and they radiate. And so over time, they lose energy and mass and ultimately disappear over huge timescales. And that's so important. This was the key in trying to understand what happens to the stuff that fell in. When you thought these things existed forever, then you think, well, it's okay, it gets locked up inside, it can never get out, we don't care. But the thing evaporates away, one day it will be gone. So then suddenly you have to be faced with this question, what happened to everything then? If I throw a book into a black hole, is it somehow possible in the far future, if you collect all this so-called Hawking radiation that comes off, is it possible to reconstruct the information in the book? That's been a question, simple question, that's driven this tremendous amount of research for 50 years. And it was pretty much solved in 2019, actually, in 2020. Well, the statement is everything comes out again, all the information comes out. So everything that fell in principle, in the far future, you could reconstruct the information of everything that fell in.
There's a supermassive black hole at the center of every galaxy.
Yeah,
but there's also other black holes that aren't necessarily in the center of galaxies.
Yeah, so these little ones, well, little, they're a few times the mass of the sun, and they're from collapsed stars. So they are stars at the end of their life, very bigger than the sun, more massive than the sun, but they run out of their fuel and they start to collapse because gravity squashes them. And if they're sufficiently massive, then there's nothing that can stop the collapse. And so they collapse, as far as we know, to a point, right, essentially an infinitely dense point. We don't really know what happens we don't know what happens right in the middle. But they collapse to such an extent that there's a region around it from which light can't escape. And so nothing can escape. And that's a black hole.
And what happens to them? Do they travel? Are they moving through space?
Yeah, they're still stars,
right?
So they're still there. They're surrounded this region where if you fall in, it's called the event horizon. And if you go across that horizon, then you are going to the center. There's one way of thinking about it, which is quite cool, which is that the time and space sort of flip is one way to think about it. So in the same way that we are going into the future now, so we're going to tomorrow. There's nothing we can do about it. We are going to tomorrow. In the same way, if you fall in across the event horizon of a black hole, you are going to the middle, the singularity it's called. So that's your future. Every line of your future points to the center of the black hole. So it's kind of the ultimate of no escape, the ultimate prison. You're going to get squashed to an infinitely dense point.
Not every star becomes a black hole at the end of its life?
No, because if something like the sun,
we have a small star.
It's quite small, yeah. And when it collapses, there's a sort of a pressure, a force, if you like, which is caused by the fact that electrons don't like to be very close to each other. So it's called the Pauli exclusion principle. But essentially what happens is that, so as they get squashed closer and closer together, they move faster and faster to sort of get out of each other's way, if you like. And that makes a force which holds them up. And so that creates what's called a white dwarf star, So you can have a blob of matter. They're about the size of the Earth, but they're about the mass of the Sun. And so that's for smaller stars. They end up as these white dwarf things, which are very dense objects. There's another version, which is called a neutron star, which is the same thing, but for neutrons. And they move faster and faster. So if it's massive enough that it overwhelms the electron thing, then the electrons sort of crush into protons and turn into neutrons, and the whole thing starts again. And so a neutron star can be, at least 1.5 times the mass of the Sun, let's say, but it can be about 10 miles across. So that's an incredibly dense ball of matter held up by the neutrons moving around. It's got a fancy name. It's called neutron degeneracy pressure, but that's what it is. But if you go even bigger, then even that can't hold it up. And as far as we know, then there's no known force that we know of that can hold the thing up if it's too massive. And so that's when it just almost winks out of existence, if you like. It collapses and collapses and collapses, and that's when you get a black hole.
You try to put that into perspective. The Sun is 1,000,000 times bigger than the Earth.
Yeah.
And this neutron star is, would you say, 1.5 times the mass of the Sun,
so
but 10 miles wide?
Yeah. So, and there's loads of those around. They're called pulsars. So we see those all over the place. The first one that was discovered was called LGM1 because they spin very fast. And it was called LGM1 because it's a very regular pulse, and they thought it was little green men. So they called it kind of jokingly Little Green Men 1. And so yeah, we've seen that there's one called the Crab pulsar, which is in the Crab Nebula, which we saw the supernova explosion. So that's when one of these stars explodes at the end of its life and then collapses to form a neutron star. And we saw that in 1054 AD. But so the Big Bang was a uniquely highly ordered, bizarrely, very strangely highly ordered thing. This is why the universe could have gone in many directions. You have to hear say the Big Bang is a quantum fluctuation. There you go, it just fluctuated and it came into existence in this highly ordered state. It's been getting more disordered ever since. But disorder, the measure of disorder is a measure of the probability that you'll spontaneously create it. So if you're very ordered, it's very unlikely you'll create it. If you're less ordered, it gets more and more and more likely you'll do it. And that's why things get more disordered. So the universe today is less ordered than it was then. So it's far more likely that it would fluctuate into existence now than it would fluctuate into existence then. Because it's less ordered now, so it's more likely. So that means that the whole universe, with us in it, having this conversation, and everything we can see, it's more likely that would fluctuate into existence than it is that the Big Bang fluctuated into existence. And it's clearly true, because it was very highly ordered then, and it's less ordered now. So you're faced with this massive problem, that if you want to say it's a quantum fluctuation, it's overwhelmingly more likely, and I mean ridiculously, billions and billions and trillions of times more likely.